This time we take on the tricky topic of membrane potential. You ever feel like you don't have much potential? I don't know, I hope you don't. But from the cell perspective, each one of your cells, specifically the membrane around it, has potential energy, which we can measure in volts. And if you multiply that around all your cells, you have 2 trillion volts, which makes the matrix make a lot more sense. Anyway, I guess based on that, I feel like I'm not living up to my potential. Sorry, that was supposed to be encouraging. Turned dark quick. Okay, let's turn this around. So, you are getting an education to build up your potential. What is potential? It's the capacity to do work, something useful. And so, each of our cell membranes do that as well. And potential energy is just stored energy, right? Like if you have this rubber band, when we stretch it, now we have stored energy. And while the purpose in doing that against our membranes is with this stored energy, it's ready to go. All we have to do is release the energy and we're off and running really fast. So that's kind of the reason behind charging up our membranes. And even though we mostly think of it in terms of the nervous system, this concept applies to every cell in the body, which is why you have 2 trillion volts worth of potential. Let's explore. There are different kinds of membrane potentials. We'll mostly focus on resting membrane potentials, but there are also graded potentials and action potentials. Now there are 2 types of tissues in our bodies that are capable of action potentials. And that would be all of our nervous system and our muscular system. Both of those types of cells and tissues are capable of action potentials, which essentially flip-flop all the ions and then put them back, which is why those 2 systems use so much energy. But first, I think we really need to concentrate on what is a membrane potential. Well, it's across the membrane, and so it's not inside and outside the cell. It's not quite that general. It's just across the membrane. So we're talking about just a few micrometers of space. And generally the outside of the cell has a slightly positive charge and the inside a slightly negative charge. We can measure this in volts, and so if we put a probe on the inside and a probe on the outside, kind of like a battery tester. I don't know if you've seen a battery tester like this one with these 2 probes, and when I touch the probes, then there's a readout, right? And it tells me that this battery has a voltage of 1.5 volts. And we can measure membrane potential as well. If I were to take these probes, like I drew there, and put them on either side, it would read an actual voltage because there's an electrical difference inside and out. So the membrane potential is basically the potential electrical energy stored across the membrane. So that's what it is. Seems strange that it's there, but that's what it is. And normally, that battery is 1.5 volts, and the cells are 70 millivolts, so 1,000th of a volt, 0.07 volts. And times 30 trillion cells in the body, that's where I came up with the 2 trillion volts throughout your entire body. It's a lot of potential energy. And every cell does it, not just the nerves and muscles. They're the ones that keep disrupting it. But all cells keep a membrane potential and maintain it at a certain point. And that point where they like to maintain it, we call that the resting membrane potential. And that's usually this 70 millivolts. Now, that's the difference across here. But since the inside of the cell is negatively charged, we usually say this is negative 70 millivolts. Yeah, but wouldn't more negative be less potential energy? Yeah, you know, it does seem like the opposite. But just because it's negative doesn't mean there's lack of potential energy. So I use this example of the rubber band. If I stretch it out, well, it doesn't matter if I stretch it in a negative direction or in a positive direction. As long as I stretch it, as long as there's a difference and some tension there, then there's potential energy. And so it doesn't matter if this is negative on the inside or negative on the outside. The more different those are, then the more potential energy. So if I had a membrane potential of negative 90 millivolts, that would even be a bigger charge. There'd be a bigger difference between the inside and the outside of the membrane. So there's membrane potential just as a basic concept. Let's get into the nuts and bolts of how the cell actually sets up this gradient. How does it store potential energy and electrical energy across the membrane? It's all about ions. And so we need to set up this electrochemical gradient. We've talked a lot about gradients, right? There's a difference between one area and another. And we got that here, the difference between the inside and the outside. We've talked a lot about chemical gradients. There's obviously going to be a difference in chemistry between the inside and the outside of the cell. But now we introduce the idea of an electrical gradient as well. So let's take a look at the big screen to talk about that. All right, so here are two different cells. Let's first tackle the chemical gradient. So here potassium concentrated inside the cell. Potassium wants to move out because of that gradient. All right, that's something we've talked about before. Electrical gradient is a little newer. So here, same sort of thing. We have particles, and we're just looking at the charge this time. There are a lot of charges outside and few inside, so these want to diffuse in. You combine the two and look at the combination of the electrical and chemical, and here we have lots of positive potassium ions, few positive, and they want to move out. There you go, electrochemical gradient. Well, let's talk a bit about the resting membrane potential, one of the types of membrane potential. This is the state where a cell it's like achieving cruising altitude. It still has to work, but it's more in just maintenance mode of keeping a charge across this membrane. So instead of drawing the whole cell, just focusing on the membrane. And a cell can kind of take it easy and just go into maintenance mode in resting potential when it has mostly sodium ions outside the cell. And inside the cell is mostly potassium ions. And there's a little potassium outside and a little sodium inside. But if it gets this difference, it's happy. It's at resting membrane potential, which is, again, negative 70 millivolts. Now, it probably seems a little strange to you that we have positive ions, and this adds up to a negative number, or really a number at all. But it's a little bit like your bank account, I suppose. Like you said, how much money do you have? Well, I have $200 in my checking account. I just got paid, so there's another $800. But I still owe $2,000 on my car, so that's negative. So net worth, $1,000. There we go. We boiled down your whole financial life to one number. So it's kind of like that for the cell. How do the positive charges up here, the positive charges down here, and everything else end up kind of summing up to a negative charge inside the cell? Well, let's take a look at the slides for that detail. To understand how the cell establishes a resting membrane potential, let's start from a really artificial state where the cell has no membrane potential. So this would be really bad. This would be a dead cell pretty much. And in this example, I'm looking at it as though this is the inside and this is the outside of the cell. And it has a zero potential because there's an equal number of sodium ions outside as inside, and same for potassium. So this is really an unacceptable state for the cell. So let's see if we can get that charge measured with our little voltmeter to a negative 70 millivolts so we can see what contributes to this resting membrane potential. Well, first, there's a bunch of proteins inside the cell, right? All kinds of stuff. Cytoskeleton, ribosomes, etc. They all have these negative charges on them, and so that contributes to some all the time, no matter where the ions go. All right, well, that's part of it, but not all of it. These potassium ions want to get into this sodium-potassium pump. We've talked about that one before. So this is our sodium-potassium pump. And it spends ATP to
to carry 2 potassiums inside, and then it dumps 3 sodiums outside. There's one round. And you can see that this has gotten even more negative. And that's because more positive ions left, leaving the inside negatively charged. Well, let's do it again. Let's spend some ATP, get more potassium inside, more sodium outside the cell. And of course, same thing happened. More positive ions left, so our cell becomes more negatively charged. And now we have a pretty good gradient going, right? We have lots of potassium inside the cell, lots of sodium outside the cell. I think this cell is looking pretty happy. It's getting close to that resting state. But we're not to -70, so what else is going on? Well, there's leak channels. So there are potassium leak channels that are just going to leak potassium, and fewer sodium leak channels. And here's where that electrochemical gradient comes in. Now, the inside of the cell is negatively charged and the outside is positively charged, right? Okay, well, potassium wants to leave because of the chemical gradient, but it wants to stay in because of the electrical gradient. But since we've built more of these potassium leak channels, it's still going to leave just somewhat reluctantly. But that sodium really wants to come in, right? It's positively charged, the inside is negative, plus it has a gradient, so both the chemical and the electrical gradient say, come on in. So we build fewer leak channels so we don't get lots of it coming back in. Part of the problem that would happen there is all that water outside would come in following the sodium and the cell would burst. Well, a little sodium came in, and then we have more of these potassium leak channels, and so that leaves. What has that done to our charge? Now we've gotten it to -70. Cell is nice and happy now. And the reason for that change is the same as before, because more positive ions left than positive ions came in. That leaves the inside negatively charged and a happy cell.
So why would a cell go to all that work? Well, to be ready for action. Again, kind of like the rubber band. Ready, go. Quick action. And I've alluded to the action potential before, how our nerves communicate and muscles contract quickly. So if the cell is all charged up, ready to go at -70 millivolts, then we can open up channels and let sodium in, which then triggers another reaction and lets potassium out. And that basically then causes a chain reaction down here, and then down here, and then down here, and the signal spreads very quickly, miles per hour, even a couple hundred miles per hour, down a neuron. So that's one application. Let's take a closer look at the action potential on a neuron itself.
So here's an extremely simplified view of an action potential. So here's our nerve cell or neuron. They're very long, and we have lots of potassium inside the cell and lots of sodium already built up outside. Again, really simplified view. And once I trigger those voltage-gated channels here, then sodium is going to come in first, followed by potassium leaving, which is going to cause a membrane potential change, which will trigger this one, which will cause a change to trigger this one, which causes a change to trigger that one. You get the idea. This is kind of what it would look like. So they move in this wave down the cell, get to the end, and what happens there is there's neurotransmitters and vesicles at the end, and that change triggers those to be released, signaling whatever other cell is over here into action.
Another way a cell could use that potential energy stored across the membrane is by using the sodium gradient to drive secondary active transport. It's been a bit, but hopefully you remember that one. So there we have glucose with a low concentration outside, but we want to bring it in where there's a higher concentration That takes energy. Well, I have energy. Because I've been pumping sodium out, it wants to come in and it can pull the glucose with it. So that gradient stores energy, which we can measure as a membrane potential, and we use that to do other types of work other than an action potential. Well, there it is. You have a lot of potential. I don't know about you, but looking at that process and how complex it is, I just have to think, I'm amazing. I hope you feel the same way. I mean, it's a complicated task, but it's not cheap. Interestingly enough, that sodium-potassium pump, one, it's unique to animals. Only the animal kingdom has it. Nobody else gets that one. It's our special membrane protein. But two, it takes a lot of energy to drive that. Because it's used in so many cells and is working all the time, it takes, some people estimate, half of your calories a day. It's probably, for most people, your breakfast and your lunch go just to feeding that sodium-potassium pump. Crazy. That sets you up really well to understand how neurons work, even muscles, but even the rest of the cells in the body. It's really pretty amazing. I hope you keep appreciating life more and more each day.